Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we have seen the continuous charge distribution and we have seen that how to find the total charge when this charge is distributed across the line surface and the volume. So in this video, first let us take the case of the line charge and let us see how the electric field is generated due to the line charge. And in the case of the line charge, how we can find the electric field intensity at the given location. So here, during our explanation, we will take the uniform charge density. So in this case, let's say the line charge density is equal to lambda L. And here, let's say the length of this charge is equal to L. So here, to find the electric field intensity due to this line charge, first let us assume that this line charge is located on the z-axis. So here, this O represents the origin. And let's say we want to find the electric field at the given location. So earlier, we have seen that if we have been given the uniform charge density lambda L, then how we can find the total charge of this line charge distribution. And we also know that for the point charge, the electric field intensity at the given location can be given by the following expression, that is equal to this Q divided by this 4 pi times epsilon naught times r square. And here, the direction of this electric field intensity is represented by this unit vector. So here, this unit vector is pointing towards the observation point at which we are finding this electric field intensity. And we know that this unit vector AR can be given as this R divided by the magnitude of this R. So that is the electric field intensity equation for the point charge. So similarly, if we have a line charge, then from the expression of the Q, we can say that this electric field intensity E is equal to this line integral of lambda L times dl divided by 4 pi epsilon naught times r square times AR. Or further, it can be written like this, because we know that this unit vector AR is equal to the vector R divided by its magnitude. So basically, here this R in the denominator represents the magnitude of the distance between the line charge and the point of observation. So basically, here what we are doing, we are taking the differential net dl on this line charge and we are finding the electric field intensity due to this differential length. And once we integrate it over the entire length of the line charge, then we will get the total electric field intensity due to this line charge at the observation point. So now, let us see how to find the expression of this electric field intensity. So here, let's say, from this differential length dl, the vector towards the observation point is equal to r. So here, for our convenience, we have placed this line charge on the z-axis. Now here if you observe, then this line charge possesses the axial symmetry, and due to which here we will use the cylindrical coordinate system. Because here, by keeping the value of z constant, if we rotate around this line charge in the fixed radius, then at the all points, the electric field intensity will remain the same. So basically, here since the line charge possesses the axial symmetry, so it is better to use the cylindrical coordinate system for our convenience. So let's say, with respect to the origin, the coordinates of the observation point is equal to rho phi z. And let's say, the coordinates for this differential length dl are rho dash, phi dash and the z dash. So here, since the line charge is placed on the z-axis, so this rho dash and the phi dash will be equal to 0. And let's say, from the origin, the distance of this differential length is equal to z dash. And similarly, let's say, this observation point is located at the phi is equal to 0. That means its coordinates are rho 0 and the z. So here, what we will do, for our convenience, let's assume that this observation point is located at z is equal to 0 plane. That means now, if we see its coordinates, then it will become rho 0, 0. That means this observation point is located on the xy plane and its distance from the line charge is equal to rho. So now, let's say, the vector that is connecting the differential length dl and this observation point is equal to r. So first of all, let us find the expression of this r, because once we know the expression, then we can easily solve this integral. So here, this line represents the origin. So from the origin, let's say the position vector towards the differential length dl is equal to r1. And likewise, from the origin, the position vector towards the observation point is equal to r2. So we can say that here this vector r is equal to r2 minus r1. So here, if we see the expression of the r2, then that is equal to rho times a rho. And likewise, this r1 is equal to this z dash times az. Because here, this observation point has only rho component, while this differential length dl only has the z component. That means here, this vector r can be given as rho times a rho minus z dash times az. And therefore, this magnitude of the r is equal to the square root of rho square plus z dash square. So that is the magnitude of the distance between this differential length dl and the observation point. So from this, we can say that this electric field intensity at the observation point is equal to this line integral of lambda L times dl times these 4 pi epsilon naught times these rho square plus z dash square raised to 3 by 2 times r, and here this r is equal to this rho times a rho minus z dash times az. So now here the only thing that we need to find is the dl. So here if you see, then the variable that we have taken for the dl is equal to z dash, because here as we move along the line of this line charge, then the value of the z dash will change. That means here we can say that this dl is equal to dz dash. That means the expression of the electric field intensity can be further written as this line integral of lambda L times dz dash times rho times a rho minus z dash times az divided by these 4 pi times epsilon naught times rho square plus z dash square raised to 3 by 2. So here if you see, then this electric field intensity will have the two component. One is the E rho, that is the radial component, and the another component is the Ez. So here if you see, then the line charge that we have taken for our example is of the finite length. So for the finite length, typically both E rho and the Ez component exist, and due to the axial symmetry, the E phi component will be equal to 0. But even with the finite length of line charge, if our observation point is at the center of this line charge, then in that case, this Ez component will get cancelled out, because in that case, due to the symmetry, the Ez component both on the top and the bottom side will get cancelled out, and in that case, we will only have the radial component. But in this case if you see, then since our observation point is asymmetric or towards the bottom side of the line charge, so in this case we will also have the Ez component. That means in our case we will have the both components of the electric field intensity. So first let us find the component E rho. So if we just consider this E rho component, then it can be written as this rho times lambda L times dz dash divided by 4 pi epsilon naught times this rho square plus z dash square raised to 3 by 2. And here let's say the limits will be from z1 to z2. So let's say the one end of the line charge is located at the z1 while the another point is located at the z2. So here to solve this integral, let us use the trigonometry. So we know that this distance is equal to rho, while if we see from the origin, then this distance is equal to z dash. So we can say that this tan theta is equal to z dash divided by rho, where this angle represents the theta. Or from this we can say that this z dash is equal to rho tan theta. So if we differentiate it, then we will get this dz dash is equal to rho times this sec square theta d theta. So here we will use this substitution. That means we will replace the z dash with the rho tan theta. And accordingly, here the integration limits will also change. So here, whenever this z dash is equal to z1, at that time, this angle will be equal to theta 1. And likewise, when this z dash is equal to z2, at that time, this angle will be equal to theta 2. So now, our new limits will be from theta 1 to theta 2. So further we can write it as this rho times this lambda L times dz dash, and here this dz dash is equal to rho times sec square theta, and in the denominator we will have this 4 pi times this epsilon naught times rho square plus rho square times tan square theta. So we know that this 1 plus tan square theta is equal to sec square theta, and therefore this term will become rho square times sec square theta, and here we also have the 3 by 2 power, so that will become this rho cube times sec cube theta. So effectively we will have integration from theta 1 to theta 2 this rho square times lambda L times sec square theta d theta divided by these 4 pi times epsilon times this rho cube times sec cube theta. So here this rho square will get cancelled out, and here this lambda L divided by 4 pi times epsilon naught is also constant. So further we can write it as this lambda L divided by 4 pi times epsilon naught times integration of theta 1 to theta 2 times 1 divided by this rho times sec theta d theta. So here this rho is also constant, so we can also take it outside, and here the 1 divided by sec theta is equal to cos theta, and we know that the integration of the cos theta is equal to sin theta. So further we can write it as this lambda L divided by 4 pi times this epsilon naught times rho times sin theta with the limits from theta 1 to theta 2, or further it can be written as this E rho is equal to this lambda L divided by 4 pi times epsilon naught times rho times sin theta 2 minus sin theta 1. So in this way we got the expression of the E rho. So similarly we will also have the another component that is equal to Ez. So now let us see how to find the component Ez. So as per our earlier expression, this Ez can be written as minus integration of z1 to z2 times z dash times lambda L times dz dash divided by this 4 pi epsilon naught times this rho square plus z dash square raised to 3 by 2. So here once again, to solve this integration, let us use the substitution. So here let's say this u is equal to this rho square plus z dash square. So if we differentiate it, then we will get this du is equal to this 2z dash times dz, because here this rho is the constant and the only variable that is changing with the integration is equal to z dash. Therefore this will become 0, and the differentiation of the z dash square is equal to 2z dash times dz. So from this we can say that this z dash times dz is equal to 1 by 2 times du. So whenever this z dash is equal to z1, at that time this u is equal to u1, and whenever this z dash is equal to z2, at that time this u is equal to u2. So with that, this Ez can be written as minus u1 to u2 times lambda L times u divided by 2 times 4 pi epsilon naught times this u to the power 3 by 2. So here if you observe, then this lambda L divided by 4 pi times epsilon naught is constant. So let us take it outside. So further we can write it as minus lambda L divided by these 8 pi times epsilon naught times integration of u1 to u2, this u to the power minus 3 by 2 times du. So we know that the integration of the u to the power minus 3 by 2 is equal to u to the power minus 1 by 2, and in the denominator we will also have the minus 1 by 2, and here the integration limits will be from u1 to u2. So further we can write it as minus lambda L divided by these 8 pi times epsilon naught times minus 2 times u to the power minus 1 by 2 with the integration limits from u1 to u2. So here this minus minus sign will get cancelled out, and further it can be written as this lambda L divided by 4 pi times epsilon naught times 1 divided by the square root of u2 minus 1 divided by the square root of u1. And here, as you know, this u2 is equal to rho square plus z2 square, and the u1 is equal to rho 1 plus z1 square. So accordingly, if we see the expression of the Ez, then this is the expression of the Ez. And earlier, we have seen that the E rho can be written as this lambda L divided by 4 pi times epsilon naught times rho times sine theta 2 minus sine theta 1. So overall, if we see the expression of the E, then that is the summation of these two components. That means if we have a finite length of line charge, then at the given observation point, the electric field intensity can be given as the summation of this E rho and the Ez. And as we have seen earlier, in the special case, when our observation point is at the center of this line charge, at that time, this Ez component will get cancelled out. And in that case, we will only have the rho component. So now, let us see the special case when this line charge is of the infinite length. So whenever this line charge is of the infinite length, at that time if you see, then both z1 and z2 will become infinite. Or to be precise, the z1 will become minus infinite and the z2 will become plus infinite. So in that case, these two components will become 0. Or we can say that for the infinite length of the line charge, this Ez will become 0. And intuitively also we can see that, because whenever the length of the line charge is infinite, then our observation point is symmetric from the both ends, and due to that this Ez component will get cancelled out. But if you see, then the E rho component will still remain. So whenever this z2 is infinite, then this angle or this theta 2 will become pi by 2. And likewise, when this z1 is also minus infinite, at that time this theta 2 will become minus pi by 2. So in that case if you see, then this E is equal to, E rho is equal to this lambda L divided by 4 pi times epsilon naught times rho times sine pi by 2 minus sine minus pi by 2. And as you know, the sine pi by 2 is equal to 1, while the sine of minus pi by 2 is equal to minus 1. So overall, we will have this lambda L divided by 4 pi times epsilon naught times rho times 2, or that is equal to lambda L divided by these 2 pi times epsilon naught times rho. That means whenever we have an infinite length of the line charge, then this is the expression of the electric field intensity at the given location, where here this rho represents the distance between the line charge and the observation point. So as you can see, as we move away from the line charge, then the electric field intensity will reduce. But if you compare this expression with the electric field intensity expression of the point charge, then in case of the point charge, the electric field intensity was reducing with the power of 2. That means in case of the point charge, this electric field intensity was inversely proportional to the r square. While in case of the line charge if you see, then here this is proportional to 1 by r. So that is the difference which we are seeing between the point charge and the line charge expression. So in short, for the infinite length line charge, this is the expression of the electric field intensity. So now, for the line charge of the finite length, let us see the different cases of the electric field based on the position of the observation point. And during our earlier discussion, the one of the case we have already discussed. So that case which I am referring is the case of the electric field whenever this observation point is along the geometric center of this line charge. So far during our discussion, we have assumed that this observation point is not passing through the geometric center of this line charge. And in general, for that case, this electric field can be given by this expression. That means in this case, the z component of the electric field will be non-zero. But now, let us see the case when this observation point is exactly along the geometric center of this line charge. So as we have discussed earlier, in that case, this Ez component of the electric field will get cancelled out. And in that case, we will only have the radial component of the electric field. And earlier as we have seen, if we further simplify it, then this zero component of the electric field can be given by this expression. So in this expression, if you see the sine theta 2, or basically if you see the theta 2, then it represents this angle. So let's say over here, the overall length of the line charge is equal to L. That means this length is equal to L. Let's say this point is at the plus L by 2 height and this point is at the minus L by 2 height. So in this case, if we see this sine theta 2, then that is equal to this L by 2 divided by the length of this hypotenuse, and that is equal to square root of rho square plus L by 2 whole square, because this length is equal to rho. Likewise, this angle represents the theta 1. So here, this sine theta 1 is equal to this minus L by 2 divided by the length of this hypotenuse, and that is equal to square root of rho square plus minus L by 2 whole square. So further if we simplify it, then the electric field intensity at the observation point will come out as this lambda L divided by this 4 pi times epsilon naught times rho times this L divided by square root of rho square plus L by 2 whole square. So this is the expression of the electric field in the case of the finite length of the line charge whenever the observation point is exactly passing through the center of the line charge. So now in the same situation, let us see the another case when the observation point is much farther from the line charge. That means whenever this distance rho is much greater than the length of this line charge. So in that case if you see, then this L by 2 whole square will be much lesser than this rho square, and therefore we can neglect this term. So further if we simplify it, then it will come out as this lambda L times L divided by this 4 pi epsilon naught times rho square. So here, if you see this lambda L times L, then that is nothing but the total charge of this line charge, and that is equal to Q. So if you see the overall expression, then that is equal to Q divided by 4 pi epsilon naught times rho square, where the rho is the distance between the line charge and the observation point. And if you see this expression of the electric field, then it is very similar to the expression which we got for the point charge. So we can say that whenever our observation point is very far away from the line charge, then in that case, this line charge can be treated as the point charge. And basically, it is the case of the far field, because in this case, our observation point is much farther from the source. So in that condition, our continuous charge source can be treated as the point charge. And that is why we are getting this expression. Alright, so now so far during our discussion, we have assumed that our observation point is not lying in the same axis of the line charge, or basically we can say that our observation point is off axis. But now, let us see the case where our observation point is lying along the same axis of the line charge. So in this case, we will see that whenever our observation point is lying along the same axis, somewhere around top or the bottom of this line charge, then in that place, what will be the electric field intensity? So if we see this case, then for this case, it is in fact very easy to find the electric field compared to the earlier case. So let's say we have one line charge And for this line charge, we want to find the electric field intensity at the some location. So once again, here we will assume that this line charge is located on the origin and it is lying on the z-axis. And here, once again, let us assume that the length of the line charge is equal to L. And here, our observation point is lying just above this line charge. That means here, this distance is equal to A. So once again, for this case, let us find the electric field intensity using this expression. So for that, let us assume some differential length dl which is lying on this line charge. And let's say this source is located at the 0, 0, z dash. Because here, since it is lying on the z axis, so the rho and the phi component will become 0. And similarly, let's assume that our observation point is also lying on the same axis. And let's say the coordinate of our observation point is equal to 0, 0, z. So here we can say that this z is equal to L plus A. So here, to solve this integral, once again, we require the value of the dl as well as the r. So here, for this differential length dl, the only variable that is changing is the z dash. Because here, during our integration, we will move along the line charge. So during that, the only variable that will change is the z dash. So we can say that over here, this dl is equal to dz dash. So now, the only thing that we need to find is the r. So here, from the origin, if you see the position vector for this differential length dl, then let's say that is equal to r1. And likewise, from the origin, if we see the position vector that is pointing towards this observation point, then that will be equal to, let's say, r2. So in this case, if we see this vector r, then that is pointing from the differential length dl towards the observation point. That means here, this vector is the r. So here, as you can see, this vector r is nothing but this r2 minus r1, right? So here, if you see the r2, then that is equal to z times az. And similarly, this r1 is equal to this z dash times az, because this height is equal to z dash. So from this, we can say that here this r is equal to z minus z dash times az. And if we see its magnitude, then that is simply equal to the magnitude of the z minus z dash. That means in this case, we will only have the z component of the electric field. And here, this Ez can be given as integration of lambda L times this dz dash divided by 4 pi times epsilon naught times z minus z dash whole cube times r. And here, this r is equal to z minus z dash. So of course, it will also have this unit vector az, but here, since we are finding the component Ez, so we are not writing it explicitly. So now, let us further simplify this expression. So in this expression, our integration limits will be from z1 to z2, where here, this z1 is the origin point and this z2 is equal to L. That means here, our integration limits will be from 0 to L. And here if you see, then in the numerator, this z minus z dash will get cancelled out. So effectively, we will have integration of z1 to z2 lambda L times dz dash divided by this 4 pi epsilon naught times z minus z dash whole square. So further it can be written as integration of 0 to L lambda L times 4 pi times epsilon naught times dz divided by z minus z dash whole square. So here if you see, then this lambda L divided by 4 pi times epsilon naught is constant. So we can take it outside. And here if you see, then the integration of this 1 divided by z minus z dash whole square will be equal to minus 1 divided by z minus z dash. And once again, here the differentiation of this minus z dash is equal to minus 1. So because of that, here we will have the plus sign. So we can say that the integration of this term is equal to 1 divided by z minus z dash, and here the limits will be from 0 to L. So here if we put the limits, then we will have lambda L divided by 4 pi times epsilon naught times 1 divided by z minus L minus 1 divided by z. So basically in this expression we have put the value of the z dash. Now as we have seen from this z is equal to L plus A. That means this z is equal to L plus A. So from this we can say that the z minus L is equal to A. That means further we can write this expression as this lambda L divided by 4 pi times epsilon naught times 1 divided by A minus 1 divided by L plus A, because here the value of the z is equal to L plus A. So further if we simplify it, then we will get this lambda L times L divided by 4 pi times epsilon naught times A times L plus A. So this is the expression of the electric field intensity whenever our observation point is along the same axis of the line charge. And further if you see, then here this lambda L times L is nothing but the Q. So we can say that here this electric field intensity is equal to Q divided by this 4 pi times epsilon naught times A times L plus A. Now in this expression, suppose this A is much greater than the L, then in that case this expression can be written as Q divided by this 4 pi times epsilon naught times A square, because in this condition this L is negligible. That means whenever our observation point is much farther away from the line charge, or whenever this A is much greater than L, then once again in that case the expression of the electric field intensity that we are getting is similar to the point charge expression. That means whenever our observation point is much farther from the continuous charge distribution, then in that case our line charge source can be considered as the point charge. And in that case the expression of the electric field intensity is same as the point charge expression. So in this way, in this video we have seen the different cases of the electric field intensity in case of the line charge distribution. So similarly, in the next video we will see that whenever our line charge source is in the form of loop, then how we can find the electric field intensity at the given location. But I hope in this video you understood how we can find the electric field intensity in case of the line charge distribution. And here we have also covered the different cases. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.